Reinforcement learning doesn't just solve problems, it teaches agents how to learn in complex, uncertain environments. This isn't about vast labeled datasets or predefined paths, it's about an agent interacting dynamically with its environment, receiving rewards or penalties, and iteratively refining its strategy. The core idea is simple: maximize cumulative reward over time, but the implications for true autonomy are immense. At its mathematical foundation, RL leverages Markov decision processes, a framework for sequential decision-making under uncertainty. The agent observes a state, takes an action, transitions, and receives a reward. This feedback loop drives the learning. The real challenge lies in estimating value functions, predicting the long-term desirability of states or actions. Algorithms like Q-learning build these estimations through temporal difference updates, learning from the difference between predicted and actual future rewards. This iterative process maps out the goodness of actions. When coupled with deep neural networks, as in deep Q networks or DQNs, RL can process high-dimensional observations like raw pixels, enabling agents to learn directly from raw sensor data. This fusion unlocks capabilities for complex perception token tasks. Consider a robotic arm learning a delicate assembly task. Instead of brittle explicit programming for every joint movement or grip force, an RL agent explores variations. It receives rewards for correctly placed components, penalties for errors over thousands of trials. It develops an optimal policy, adapting to slight variations in part orientation or minor environmental shifts. This approach starkly contrasts traditional control systems, which demand extensive domain expertise and meticulous manual modeling. Unlike supervised learning, which needs labeled data, RL learns from its own experience. Unlike evolutionary algorithms, RL maintains memory and updates policies incrementally, uniquely suited for sequential decision-making. It allows systems to discover optimal, often counterintuitive behaviors. A critical, rapidly evolving trend is simtorial transfer, training complex RL policies entirely within highly realistic simulations, then deploying them directly onto physical robots. This bypasses the cost and safety concerns of real-world data collection. By employing domain randomization, varying simulation parameters, agents learn policies robust enough to generalize to the subtle discrepancies of the physical world. It's a potent bridge between virtual and tangible reality. Ultimately, reinforcement learning moves us beyond mere automation, towards genuine autonomy. It's about building systems that don't just execute instructions, but dynamically adapt, explore, and discover optimal strategies within the rich, often chaotic realities of their environment.